Welcome to another deep dive. Today we're turning our attention to some really fascinating research projects,
Hmm.
specifically the ones developed by the Applied Computing Research Group.
Right, the GCA.
Exactly, better known as the GCA. And we're looking at a highly comprehensive study authored by a really stellar team of researchers.
Yeah, that's Daniela Elfrere, Raphael Z. France, Fabricio Ruiz France, and Sandro Sawicki.
Right. And to really understand the scale of what they are tackling here, I want you, the listener, to just imagine a scenario for a second. Imagine you are the chief technology officer of a massive global corporation. I mean, we're talking tens of thousands of employees, millions of daily active
A
customers.
total behemoth.
Exactly. And over the last 2 decades, your company hasn't just grown, it has, mutated.
Oh, yeah. Growth by acquisition is always messy.
Right. You've acquired 3 rival companies, and each of them comes with their own entirely alien tech stacks.
Which is a nightmare.
Complete nightmare. You've migrated half of your active user data to a cloud environment, but you've left your highly sensitive legacy financial records on bare metal local servers.
As you do, for security.
For security, yeah. But none of these systems were ever designed to acknowledge the existence of the others.
No, of course not. They were built in silos.
Right, so you have an HR swirt from, say, 2005 trying to communicate with a cutting-edge cloud-native CRM.
Oh, wow.
Yeah, while a bespoke, completely duct-taped inventory tracker desperately tries to ping both of them in real time. So the question is, how do you keep the entire ecosystem from just, imploding under the weight of its own data requests?
Well, what you're describing there is really the defining architectural nightmare of modern enterprise computing.
Is it that common?
Oh, it is incredibly
Okay.
common. I mean, we just don't have single, elegant software machines anymore.
Yeah.
We are dealing with environments that are, by their very nature, these heterogeneous hybrids.
Hybrids, okay.
Yeah, and the friction between these disparate systems is immense. Trying to get a legacy embedded system to seamlessly sync with, like a high-velocity cloud cluster,
It's gotta be tough.
it's a bit like trying to power a modern Tesla engine by shoveling coal into a 19th century steam boiler.
That is a wild image.
Right. But the interfaces just don't match. The latency expectations are wildly different. And the sheer volume, variety, and velocity of big data flowing between them, it just threatens to bottleneck the entire operation.
So what stops that from happening?
Well, the only thing standing between that business and total operational failure is an enterprise application integration platform.
An EAI.
Exactly, an EAI. And the GCA team's research mission here is really critical because they have developed this rigorous, mathematically structured methodology to rank these integration platforms.
Oh, interesting. So they're ranking them.
Yes, but they are cutting through the vendor hype entirely.
No marketing fluff.
None. They are assessing them purely on the raw performance of their runtime systems.
Okay, let's unpack this, because the runtime system is really the heart of the matter here, right?
Absolutely.
Like, if we use the classic analogy of an air traffic controller, the software engineers use domain-specific languages to design the conceptual models,
Right.
which is basically drawing up the theoretical flight paths on a static map, right?
It's a good way to put it, yeah.
But the runtime system is the actual controller sitting in the tower. They're actively executing those data synchronizations, dynamically routing the messages, and, actively preventing mid-air collisions.
Right. Between, say, an inventory update and a point-of-sale transaction.
Exactly. It is where the theoretical architecture hits the actual real-world workload.
Yeah.
So if raw execution performance is so vital to keeping the enterprise afloat, I guess my question is, why does this study even need to exist?
What do you mean?
Well, aren't CIOs already evaluating EAI platforms based on their runtime throughput? I feel like that should be step one.
You would assume so, right.
Hmm.
But that is actually the massive market disconnect the researchers are addressing here.
Really?
Yeah. When companies are looking to invest, millions of dollars into an integration platform, they almost invariably default to consulting firm reports.
Oh, like the Gartner Magic Quadrant?
Exactly. Gartner or Ovum decision matrices.
Right.
And those reports are undeniably useful, don't get me wrong. But they heavily weight factors like vendor market presence
Oh.
or the historical maturity of the provider, customer relationship management, and upfront pricing.
So they're measuring the corporate shell around the software.
That is exactly it.
Hmm.
And the GCA researchers argue that this is structurally backward.
I mean, that makes sense.
Right, because the runtime system's performance, its ability to consume the absolute minimum computational resources while processing the absolute maximum throughput of messages, that has to be the foundational requirement.
Because if the core doesn't work,
If your core processing engine is inherently inefficient, it does not matter how good the vendor's customer support hotline is.
yeah, that's fair.
When Black Friday hits, and your data volume spikes by 400%, a polite account manager cannot stop your data flow from backing up and failing.
Yeah, that makes perfect sense. But if I put myself in the shoes of a procurement team measuring provider maturity or just looking at a pricing sheet, that's easy.
It's very easy, yeah.
But benchmarking the granular efficiency of a runtime system across totally disparate architectural philosophies, that seems impossibly complex.
It is incredibly difficult.
Like if you were comparing an event-driven architecture against a traditional process-based one, you aren't just comparing apples and oranges.
Right.
You are comparing apples to, say, a hydraulic press.
That's a great analogy.
How do you objectively measure the efficiency of thread management against the fairness of a specific scheduling policy? It feels like the moment you try to quantify those variables, you just end up relying on the subjective bias of whatever software engineer happens to be leading the evaluation.
And that is the exact trap. That is the precise reason this study relies on a structured decision-making framework. Because when you throw 20 different technical variables at a human brain and ask for a definitive ranking, the human brain just short circuits.
We just can't handle it.
No, we default to tribalism. An engineer will simply recommend the platform they used at their last job just because it feels familiar.
Oh, of course. I know this one, let's buy it.
Exactly. So to neutralize that cognitive bias and to handle the extreme mathematical complexity of comparing, apples to hydraulic presses,
Yeah.
the researchers utilized a methodology called the Analytic Hierarchy Process, or AHP.
Right, AHP. Tomasetti developed this back in 1990, I think.
Yes, exactly, 1990.
And if you have ever sat in a brutal procurement meeting, just staring at a spreadsheet of 5 different vendors and feeling your eyes glaze over, you know exactly why AHP is necessary.
It's overwhelming.
It is, and it acknowledges this fundamental psychological reality, which is that human beings are biologically terrible at evaluating 10 complex variables simultaneously.
We really are.
But we are incredibly sharp when we are asked to compare just 2 things at a time. So AHP takes that overwhelming multivariable spreadsheet and structurally models it as an inverted tree.
Structuring the problem is really half the battle here.
Right.
So at the top of that inverted tree is the ultimate goal, which in this case is selecting the EAI platform with the highest runtime performance.
Okay, that's the trunk or the root of the tree.
Exactly. You then move down to the branches, which represent the criteria. The study calls these the dimensions of performance.
Got it.
And finally, you reach the leaves at the very bottom, which are the alternatives, the specific platforms under evaluation.
Right.
And by breaking the architecture down this way, AHP allows engineers to utilize what are known as pairwise comparisons.
Right, pairwise comparisons. I look at those almost like a massive sports tournament bracket.
Oh, that's a good way to visualize it.
Yeah, because instead of looking at a field of 64 teams and trying to magically rank them from 1 to 64 in your head, you just ignore the wider field entirely.
You focus on the single game.
Exactly. You just look at the head-to-head matchup in front of you. Does Platform A beat Platform B regarding this one? Highly specific technical criterion.
Yes.
And the researchers use a 1 to 9 scale for this, correct?
They do, yeah.
Where 1 means the 2 platforms are equally competent, 3 is a moderate preference, all the way up to 9, which indicates one platform is demonstrably extremely superior to the other in that specific matchup.
Yeah, that's exactly how the scale works. But what's fascinating here is that the AHP methodology doesn't just record these subjective 1 to 9 scores.
It doesn't.
No, it actively interrogates them for logical consistency.
Oh, wow. How so?
Because even in a one-on-one comparison, humans are notoriously inconsistent.
That is very true.
Let's say you evaluate 3 platforms, right? In your head-to-head matchups, you state that Platform A is far superior to Platform B.
Yep.
Later, you rank Platform B as slightly better than Platform C.
Makes sense so far. A beats B, B beats C.
Right, but hours later, when A and C go head-to-head, you get confused by a specific feature, and you claim Platform C is actually better than Platform A.
Oh. You've just created a circular logical paradox.
Exactly.
The transitive property just completely breaks down.
Precisely. And to catch this, AHP calculates a consistency ratio, using matrix algebra.
Matrix algebra. Okay, my brain is already hurting slightly.
No, without getting bogged down in the formulas, just think of the decision matrix like a massive, highly interconnected Sudoku puzzle.
Okay, I can do Sudoku.
Right. If you place a number 9 in a box where the underlying logic dictates a 2 should go, it doesn't just affect that single box.
Right, it ruins the whole row and column.
Exactly. It fractures the mathematical integrity of the entire grid. By calculating the principal eigenvalue of that matrix, the system measures the exact severity of the fracture.
So it knows exactly how inconsistent you're being.
Yes. And if the consistency ratio creeps over 0.1, the mathematical framework literally rejects the human input.
Wait, really? It just says no.
It tells the engineering team, your logic is flawed, you are contradicting your own baseline preferences, go back and reevaluate.
That is brilliant.
It is a built-in mathematical lie detector for human cognitive bias.
I love that. It forces absolute mathematical rigor onto a process that usually just relies on gut feeling.
Exactly.
So, having established this incredibly strict framework, we need to look at what exactly the researchers are feeding into the matrix, right? Like, what are the actual criteria for good performance?
Right, the dimensions.
Yeah. The study breaks runtime performance down into 3 foundational pillars, and they assign strict weighted multipliers to them. The heaviest weight is given to the essential pillar, which is message processing.
Right, that one is critical.
It gets a multiplier of 3. So let's look at the properties they explore here, starting with thread pool creation, because any systems architect knows that thread starvation can bring an enterprise to its knees.
Oh, absolutely.
So how are they evaluating the way these platforms handle threads?
Well, the evaluation heavily penalizes the use of a global thread pool.
Okay.
And it heavily rewards local thread pools.
Why is that? What's the difference?
If an integration platform relies on a global thread pool, it means it is dumping every single processing request into one massive shared queue.
Just one big bucket.
Right. And the risk there is obvious. If you have a suddenly heavy, complex task, say, a massive batch processing request from that legacy HR system we mentioned earlier,
Yeah.
it can monopolize the entire global pool. It hogs all the available threads, and smaller, hypercritical, time-sensitive messages from the CRM are just left starving in the queue.
Because the HR system is taking up all the oxygen in the room.
Exactly.
Yeah.
But a local thread pool strategy allows the system to isolate and dedicate specific worker pools to specific distinct tasks.
Oh, okay.
It guarantees that a massive data dump in one part of the enterprise cannot cannibalize the compute resources needed for real-time operations in another.
I see. It's the difference between having one massive chaotic line at a grocery store versus having dedicated express lanes.
That's exactly it.
You need to keep the high-velocity data moving.
Right.
Okay, so the second property in this essential pillar is message storage. How does the system physically hold the data while it routes it?
Yes.
And the 2 options evaluated are in-memory versus hybrid storage. Obviously, keeping data in memory is the fastest possible option for the CPU, but it introduces a massive fragility when dealing with enterprise-scale payloads, doesn't it?
It introduces a critical point of failure, yes.
Right.
In-memory storage is incredibly fast, but RAM is finite, and it's expensive. If an EAI platform only supports in-memory storage, it is basically assuming a relatively predictable, controlled volume of data.
Which never happens.
Never. Enterprise environments are defined by the unpredictable volume, variety, and velocity of big data.
Yeah.
If a system experiences an unexpected massive spike in throughput, an in-memory-only platform will simply hit its ceiling and crash. It will just start dropping critical messages.
As a disaster.
A total disaster. So a hybrid storage system is preferred in the matrix because, while it leverages memory for speed, it possesses the architectural elasticity to seamlessly offload messages to persistent disk storage or dedicated databases when those volume thresholds are breached.
Ah, so it has a backup plan.
Exactly. It sacrifices a microsecond of speed for a massive gain in systemic resilience.
And that brings us to the third property under message processing, which is thread pool configuration.
Right.
Does the platform use static or dynamic configuration? Static means an engineer manually hard codes the thread count, right? Like maybe they provision 100 threads for a task, and that is what the system is locked into, regardless of the actual traffic.
That's right.
And dynamic means the runtime system monitors its own workload and can autonomously spin up new threads during a traffic spike or spin them down to conserve resources during a lull.
Precisely.
But here is where I have to push back a little bit on the reality of the market versus the theory of the paper. Yeah, because reading the study, None of the 5 major open source platforms they evaluate actually possess dynamic thread configuration.
That is correct.
They're all entirely static. Doesn't this represent a massive vulnerability in modern enterprise software if everyone is just stuck on static?
It absolutely represents a vulnerability. And, it highlights a really fascinating lag between theoretical computer science and open source reality.
Why is there a lag?
Because dynamic thread configuration is notoriously difficult to implement safely.
Really?
Oh, yeah. If the scaling algorithm isn't perfect, the system can actually consume more CPU overhead just trying to manage the creation and destruction of the threads than it spends processing the actual messages.
Oh, so
Yeah.
the management becomes the bottleneck.
Exactly. It's a phenomenon known as thrashing.
Thrashing.
Yeah. So the maintainers of these major open source platforms have essentially decided that the risk of thrashing outweighs the benefits of elasticity.
So they just don't offer it.
Right. They force the human architects to over-provision static threads to handle potential peaks.
I see.
The methodology correctly identifies dynamic as the superior theoretical property, but it also rigidly highlights that the current market is universally failing to provide it.
That is a very sobering reality check for the industry.
It really is.
Okay, moving to the second pillar of performance, we have fairness execution.
Right. Fairness execution.
The researchers classify this as important, giving it a weight multiplier of 2.
Mm-hmm.
The goal here isn't just raw speed. It's about minimizing the average processing time across the board by ensuring computational resources are distributed fairly.
Fairly.
The first property they evaluate here is the core execution model, process-based versus task-based.
And the distinction here fundamentally alters how the system behaves under pressure.
How so?
Well, in a process-based execution model, the system takes an entire complex integration route and tries to execute it as a single uninterrupted sequence from start to finish.
Okay, so it holds on until it's done.
Right. If one step in that long process requires a massive database query, the entire process halts. It holds on to all its system resources while it waits.
Oh, so it just blocks everything else.
Yes. But a task-based model, which the matrix scores higher, breaks that route down into highly granular, independent steps.
Ah, I see.
It executes step 1, releases the resource, executes step 2, and so on.
So in a steady stream enterprise environment, task-based execution prevents those complex, long-running integrations from monopolizing the CPU.
Exactly. It stops them from blocking simpler, faster messages from completing.
The flow state is much more fluid that way.
Much more fluid, yes.
This pillar also looks at scheduling policies, right? Like FIFO, priority, and mapping.
Yes, exactly. FIFO is first in, first out, which is standard but rigid. Priority lets critical messages jump the line, and mapping allows for specific routing based on content, which gives you much more control.
Right. And then there's a really interesting property they evaluate here, the presence of a throttling controller.
Oh, that's a big one.
I find this fascinating because it essentially acts as a system's survival instinct.
Yes.
If the EAI platform detects that the inbound message volume is exceeding its absolute processing capacity, a throttling controller allows it to automatically reject or delay incoming requests. Right?
Yes.
It deliberately degrades service to external endpoints to prevent the core runtime environment from total memory exhaustion and a hard crash.
Exactly.
It sacrifices the few to save the many.
If we connect this to the bigger picture, a throttling controller is the ultimate acknowledgement that enterprise systems operate in a hostile environment.
Hostile.
Well, you cannot always trust the system sending you data to behave predictably.
Ah.
Without throttling, a compromised or even just a malfunctioning external application could inadvertently launch a denial-of-service attack against your integration platform.
Just by sending too much normal data.
Yes, just by spamming it with legitimate but overwhelmingly voluminous requests.
Wow.
So the AHP matrix rightly rewards platforms that prioritize self-preservation over blind ingestion.
That makes total sense. Which perfectly transitions us into the third and final pillar, hotspot detection.
Right.
This is weighted as desirable with a multiplier of 1, and it is all about how the system identifies bottlenecks.
Yes.
Does it rely on design time detection, where a human engineer has to artificially simulate loads and guess where the traffic jams will happen before the system goes live? Or does it offer runtime detection, where the platform actively monitors its own telemetry in production and flags bottlenecks as they occur organically?
And runtime detection is the absolute gold standard here.
I would assume so.
Yeah, because design time detection is inherently flawed.
Because it's just guessing.
Well, staging environments almost never accurately replicate the true chaotic variables of a live production environment.
Oh, true.
You can simulate traffic all you want, but you cannot perfectly simulate the unpredictable network latency of a third-party API that your system relies on.
You can't simulate chaos.
Exactly. A platform that can identify a hotspot organically during runtime allows administrators to react to reality, rather than relying on theoretical foresight.
Which is huge.
It is. Interestingly, the study also looks at the abstraction level for this, whether you're analyzing bottlenecks by an entire group of routes or down to the individual task level. Task level is obviously much better for pinpointing the exact issue.
Right. And what about pattern identification?
Ah, yes. That's whether the system can autonomously recognize behavioral sequences that typically precede a bottleneck.
And spoiler alert for the listener, just like with dynamic thread configuration, the paper reveals that currently none of the major platforms evaluated can actually do pattern identification.
Yeah, unfortunately.
We are still relying heavily on human intuition to interpret the telemetry data.
Oh, no, yes.
So, having rigorously defined these three pillars, message processing, fairness execution, and hotspot detection, how exactly do we merge this deep technical criteria with the subjective human scores we talked about earlier?
Right, bringing it back to the AHP.
Yeah, this brings us to the scoring mechanics, the actual man versus machine collision of the methodology.
Well, the researchers devised a really brilliant mathematical synthesis for this.
Okay.
The final score for any given platform within a specific criterion is not just a single number.
It's not.
No, it is the sum of two distinct values. First, the subjective consensus derived from the human pairwise comparisons.
The 1 to 9 scale.
Exactly. Plus, an objective score based on the hard architectural realities of the platform.
Okay.
And that combined sum is then multiplied by the weight of the dimension.
Right. The times 3 for essential, times 2 for important, times 1 for desirable.
Exactly.
But the objective score is where the methodology really shows its teeth, I think.
Oh, definitely.
Because the human experts are restricted to that 1 to 9 scale.
Right.
But the objective criteria, the hard architectural facts, like whether a platform uses a task-based execution model or a local thread pool, those are scored on a massively inflated scale of 1, 10, or 100 based on preference order. By doing this, the researchers intentionally built a mathematical trump card into the system.
It is a critical failsafe.
Why is it so necessary?
Well, think about what happens if you don't inflate the objective score.
Okay.
Let's say a team of engineers is evaluating two platforms. Platform A has a vastly superior, highly resilient hybrid storage architecture.
Which is an objective fact.
Yes, an objective fact. But Platform B is built on a framework the engineers have used for 10 years, and they simply feel more comfortable with it.
Which is pure subjective bias.
Exactly. Now, if both the subjective and objective scales are weighted equally, the engineer's biased 9 out of 9 score for Platform B could easily cancel out Platform A's objective architectural superiority.
Oh, I see. They could just outvote the facts.
Yes. By scaling the objective hard-coded capabilities at 10 or 100, the methodology ensures that factual system capabilities will always mathematically overpower the nostalgic preferences or subjective biases of the human evaluators.
It essentially prevents human operators from accidentally sabotaging their own infrastructure out of habit.
That's a perfect way to phrase it.
So what does this all mean when we drag it out of the theoretical realm and apply it to real-world technology?
This is where it gets really fun.
Yeah, because the GCA researchers selected 5 highly popular open-source integration platforms to run through this massive crucible. We are looking at Spring Integration, Camel, Fuse, Petals, and Guarana.
Yes.
And to give the listener some baseline context, all 5 of these platforms rely on the conceptual pipes and filters architectural style, right?
They do, yeah.
Meaning they take complex data processing and break it down into independent filters connected by routing pipes.
Exactly.
But the way their runtime engines execute that architecture varies wildly.
Oh, absolutely wildly. And the divergence becomes immediately apparent when we look at the essential pillar, message processing.
The one with the ×3 multiplier?
Right. Spring Integration and Camel instantly take a massive lead here.
Why is that?
Because their underlying architectures support local thread pools and hybrid message storage.
Ah, so they check those objective boxes.
Yes. They are built for enterprise resilience. Petals and Guarana, conversely, are architecturally restricted to global thread pools and in-memory storage.
So they're getting hammered in the scoring.
From a purely mathematical standpoint within this framework, yes. Petals and Guarana are immediately penalized because they inherently risk thread starvation and memory exhaustion under massive payload spikes.
Right out of the gate, that heavy times 3 multiplier on the essential pillar starts separating the pack.
It really does.
But when we look at hotspot detection, the landscape shifts dramatically.
It does.
Camel absolutely dominates this dimension, doesn't it?
Oh, completely. It is the only platform among the 5 capable of genuine runtime bottleneck detection.
Wow, the only one?
Yeah, the others force administrators to rely on design time foresight, which we already established is flawed.
Right. But Guarana does manage to claw back some points here, though.
It does.
Because while it doesn't have runtime detection, its abstraction level allows engineers to monitor telemetry on a per-task basis.
Yes, whereas platforms like Spring only allow monitoring on a per-group basis.
So Guarana gives you a much finer microscope, even if you still have to look through it manually.
Exactly, and that granular control is exactly why Guarana really shines in the fairness execution pillar.
Oh, okay.
Guarana is the only platform evaluated that utilizes a strictly task-based execution model.
Oh, interesting.
The others rely heavily on process-based execution.
Right, holding the whole route hostage.
Exactly. Although Camel does attempt to mitigate this by implementing a highly complex, asynchronous staged, event-driven architecture.
That sounds like a mouthful.
It is, but it helps. However, Camel and Spring pull ahead in this dimension once again.
Because of the throttling controllers?
Yes, because they feature robust throttling controllers.
Ah.
Guarana, for all its elegant task-level execution, lacks that core survival instinct to throttle incoming traffic when overwhelmed.
This raises an important question for you, the listener. If you were the CTO making this call without the AHP matrix to guide you, what would you prioritize?
It's a tough call.
Would you pick the raw, heavy-duty processing power and survival instincts of a platform like Spring, or the incredibly deep, granular, task-level execution control of Guarana?
Right.
It is brutally tough when you are just staring at feature lists, but we have the matrix.
I do.
The subjective pairwise comparisons are mathematically verified. The objective 10 and 100-point scores are locked in. Everything is multiplied by its weighted dimension. When the researchers finally tallied the massive aggregated scores, the definitive ranking emerged.
And the numerical gap in the final results is striking. It thoroughly validates why subjective evaluation alone is insufficient.
Here's the final breakdown.
Jerome, please.
In first place, with a commanding lead, is Camel with 135 points.
Wow.
Second place goes to Spring Integration with 123 points.
Close, but not quite.
Right. Then we have a massive drop-off to a tie for third place between Guarana and Fuse, both sitting at 60 points.
That's a huge gap.
It really is. And in dead last, severely penalized by its architectural limitations, is Petals with just 24 points.
Ouch. So let's dissect exactly why Camel took the crown here.
Yeah, how did it win by that margin?
It didn't win by being marginally better at everything. It won through a massive compounding of critical architectural choices.
Because of the weights.
Exactly. Because message processing was deemed the essential pillar and weighted 3 times heavier than the others. Camel and Spring's objective scores, which were derived from their use of local thread pools and hybrid storage, skyrocketed their baseline numbers.
So they just left the others in the dust immediately.
They essentially mathematically eliminated the other 3 platforms right there.
Wow.
But the absolute deciding factor, the reason Camel edged out Spring by 12 points, was Camel's exclusive ability to perform runtime hotspot detection. That singular capability, even though it was in the lowest weighted desirable dimension, provided the exact mathematical margin of victory.
That is fascinating, but here's where it gets really interesting, though. The researchers are very careful to point out a major caveat to all of this.
Yes, very important to note.
This specific ranking Camel at 135, Petals at 24, is not an absolute immutable law of physics for every single company on Earth.
No, not at all.
The true value of this study isn't just handing you a winner, it's handing you the methodology itself.
Exactly. The AHP framework is inherently flexible.
How so?
Well, let's say you operate in a highly specific, highly regulated environment, maybe high-frequency financial trading.
Right. Okay, where speed is literally everything.
Exactly. In that environment, minimizing average processing latency is vastly more critical than overall mass throughput.
Right.
So in your specific corporate matrix, you might decide that fairness execution is the essential times 3 pillar, and message processing is merely desirable.
Oh. And if a corporation shifts those baseline weights, the entire mathematical topology of the results changes instantly.
Instantly. If fairness execution becomes the dominant multiplier, a platform like Guarana, with its incredibly granular task-based execution model, suddenly shoots up the rankings. It could potentially overtake Spring, or even Camel, depending on how aggressively you penalize global thread pools.
That is amazing. The genius of the GCA's work isn't that they found the best software, it is that they built an adaptable, mathematically bulletproof engine for justifying enterprise architecture decisions.
That's the real takeaway here.
Think about the real-world application of that. When you, as a tech leader, have to walk into a boardroom and ask the CEO and the board of directors for a $10 million budget allocation to rip out and replace your entire enterprise integration layer.
Good luck with that.
Right. You cannot walk in with a Gartner report and say, well, they have a really nice customer service portal.
You will be laughed out of the room.
Completely. But if you walk in with this AHP matrix,
That changes everything.
if you can show them that you mathematically neutralized your engineering team's biases, evaluated the hard architectural realities of the runtime systems, and mathematically proved that Platform X will prevent the specific thread starvation bottleneck that caused last year's Black Friday outage. That is how you secure an IT budget. You transform a highly subjective technical debate into an undeniable mathematical proof.
It shifts the paradigm from qualitative preference to quantitative certainty.
Exactly.
It forces software vendors to compete not on the glossiness of their marketing brochures, but on the ruthless, invisible efficiency of their runtime code.
We have covered massive ground today.
We really have.
We started with the absolute chaos of a fragmented Frankenstein-style corporate software ecosystem. We looked at how the GCA researchers took the Analytic Hierarchy Process, a tool designed to prevent human cognitive overload, and applied it to the invisible, high-stakes world of runtime performance.
Right.
We broke down the essential need for local thread pools and hybrid storage, the fairness of task-based execution, and the holy grail of runtime hotspot detection.
Yeah.
And we saw how mathematical weighting can decisively crown a platform like Camel, while completely exposing the limitations of platforms reliant on global thread pools.
It's quite a journey.
It is, but I want to leave you, the listener, with a final thought, something to just, mull over outside the realm of enterprise software entirely.
Okay.
We have spent this whole time discussing how the analytic hierarchy process structures overwhelming corporate decisions. But strip away the software jargon.
Sure.
At its core, AHP forces you to take a massive, anxiety-inducing choice, break it into essential, important, and desirable weights, and then mathematically audit your own psychological consistency by only comparing two variables at a time.
It's a powerful tool.
So what massive, overwhelming decision are you currently facing in your own personal life or your career?
That's a great question.
Are you relying on the Gartner report of other people's opinions? What would happen if you applied this exact mathematical matrix to that decision today, forcing your own objective realities to overrule your subjective biases?
I think people would be surprised by the results.
I think so too. Thank you for joining us on this deep dive. Keep questioning the consensus, keep looking at the underlying architecture of the problems you face, and we will see you next time.